Hi, I'm Kusha and my groupmate Nicholas. Today we'll be talking about abalones and the summary of main goals in this project. First, we aim to identify the key factors that contribute to abalone age using biological and physical measurements. Second, we evaluate the predictive accuracy of multiple linear regression models and compare them with a regularized elastic net approach to understand trade-offs between interpretability and performance. And finally, we integrate these analyses into an interactive or shiny dashboard along with a RAG assistant to make the results transparent, reproducible, and easy to explore. Here we show the summary of the features in the dataset used for analysis. Target variable is age. The input feature includes one categorical variable, sex, and several continuous physical measurements. These measurements fall into two groups: size-related features, such as length, diameter, and height, and weight-related features. In addition, log transfer versions of the weight features are created to improve linearity and model performance, particularly for the ElasticNet model.
So right here, we're getting an idea of the age distribution by sex, and it's very important to note that there's three different distributions here, and that's because sex is non-binary in this data set. So there's an infant, a male, and a female outcome for the sex variable. Morphological versus biomass features, and on the left here, we have the height versus age by sex. And you see it's more tightly grouped and there's more of a linear relationship there when on the right, if you look at it, there's the residuals are more spread out and there's less of a linear relationship that we could draw from that. In those past few slides, we had some hypotheses that we wanted to test out real quick using simple linear models. And actually, even though the sex is non-binary, even though some of the variables are measured differently through different units, some are measured through millimeters, some are measured through grams, actually the lowest MAE thus far would be all of the variables in the full data set. That MAE even lower. And so we're to be harping back on how the residuals were so spread out on the weight distribution versus the age. And if you see on the left here, the raw weight versus the age is more spread out, less of a linear relationship. But when you take the log transformation of that weight versus age, you can see a tighter spread and less residuals and more of a linear relationship from that. Right here, we wanted to take everything that we've done up to this point, and we wanted to try out 5 different models and 5 different normalization combinations and see kind of what's given us the lowest MAE. And so the elastic net model with the raw data meaning the log transformation data, but no normalization method would actually yield us the lowest MAE at this point.
At this stage, we introduce our engineered features, including the log transform weight variables, as well as derived measures such as volume, density, and log density. These features help capture growth patterns that are not strictly linear. When we apply a linear regression model with elastic net regularization, which combines an L1 penalty for feature selection and L2 penalty to stabilize estimates under multi-collinearity. Using this approach, the model achieves a mean absolute error of 1.411, indicating a strong predictive performance.
I talk too much about models that we actually won't be presenting on today, but I do want to mention that within the code contents, there are an XGBoost model with hyperparameter tuning, and it sort of has a gradient boosting framework that can capture some nonlinear relationships, even on an elastic net might miss. And for the second one, it would be the leave one out cross validation models. And those have sort of become a gold standard for small data sets like this.
What we built is a CPU-based RAG system that answers abalone FAQ questions directly from PDF sources. The system generates accurate, source-faithful, and paraphrased responses, ensuring the answers are both reliable and easy to understand. This table outlines the four main steps used in the RAG application, from PDF ingestion to robust chunking to semantic retrieval, and lastly to two-stage answering, and finally the encoder and generator models that we use in the app to produce accurate and source-grounded responses. As you can see, the encoder is the All-Mini LM L6v2, and the generator is Google Flan T5 base. Here we showed a sample RAG response to a common question about abalone mortality in farms, with answers grounded in the source PDFs. This is my abalone age prediction and modeling dashboard built in R-Shiny. The workflow starts by uploading the abalone CSV file on the left, and the controls automatically adapt based on the active tab. The visualization and EDA tab focuses on understanding the data before modeling. Here I explore distributions by sex, correlation with age, and scatter plots of age versus numeric features. I can also filter by sex and optionally apply log transforms to weight variables to better linearize relationships. The model tab applies two approaches, multiple linear regression and elastic net, both evaluated by 5x5 cross-validation. For each model, the app shows performance metrics, coefficient tables, and diagnostic plots. The compare view allows direct comparison of metrics, residual behavior, and variable importance between models. The data preview tab provides a quick check of the uploaded dataset in a scrollable table. Finally, the Abalone PDF RAG Assistant tab embeds a retrieval augmented assistant that answers abalone-related questions directly from the curated PDF documents. Overall, this app integrates exploratory analysis, robust modeling, and documentation support into a single interactive dashboard. Thank you for your attention. If you have any questions, please reach us at these two email addresses.